Hey everyone, and welcome. Today, we're going to pull back the curtain on the invisible forces that power so much of our world. We're talking about alternating current, and we're about to see how what looks like total electrical chaos can actually create, well, perfect harmony. I mean, seriously, think about that for a second. There are countless radio signals floating all around you right this minute. So how does one simple device zero in on just one? It's not magic, but man, it sure feels like it, right? Well, that secret is locked away inside the physics of AC circuits. And by the time we're done with this explainer, you are going to have the key. So let's get started. All right, first things first, we got to get to know our main character here, alternating current, or AC. And the best way to do that? Put it side by side with its sibling, direct current, or DC. Okay, so here's the absolute key difference. DC power, like from a battery, is the super steady one-way street where the voltage just holds constant. But AC power, the stuff from your wall outlet, totally different ballgame. Its voltage is constantly changing, swinging back and forth, kind of like a wave. So you might be thinking, if AC is always changing, how in the world do we even measure its power? Like, what's a useful number? Well, we use something called the RMS, or root mean square value. It's basically a super clever way of asking, hey, what's the DC equivalent of this AC source? It gives us a solid, workable number. Let's make this real with a quick example. So as you can see, if a circuit has a peak current of 10 amps, its effective, or RMS current, isn't 10. Nope. We divide it by the square root of 2, and that gives us an RMS value of about 7 amps. That is the number that tells you how much real work that current can actually do. All right, so we've got a handle on AC. Now let's meet the three key players that make these circuits so fascinating: the resistor, the capacitor, and the inductor. And trust me, each one has its own unique personality. First up, we've got the resistor. This is the simple, no-nonsense one in the group. In a resistor, the current and voltage are always in perfect lockstep. They rise together, they fall together. We call this being in phase. Super simple, super predictable. Okay, next we have the capacitor. Its job is to store and release energy. You can kind of think of it like a tiny rechargeable battery that needs a moment to charge up. And because it takes that time to charge, the voltage across it actually falls behind the current. It's always playing catch up, so we say the voltage lags the current. And that brings us to our final player, the inductor. An inductor is all about inertia. It hates sudden changes in current, and it fights against them. This fight, this resistance, actually gives the voltage a head start, causing it to peak before the current does. So for an inductor, the voltage leads the current, the total opposite of the capacitor. So, what happens when we throw all three of these components, with their totally different personalities, into one circuit together? Well, that's where the magic really starts. This setup is called an LCR circuit, and when all three are working together, they create this total combined opposition to the current. It's way more complex than just simple resistance, so it gets its own special name, impedance, and we represent it with the letter Z. Okay, so how on earth do we calculate this total impedance? We can't just add everything up. Remember how the inductor and capacitor are total opposites? Well, they're in this constant tug of war. This diagram here shows it perfectly. The opposition from the inductor and capacitor, we call that reactance. They're pulling up and down on that vertical axis. Meanwhile, the good old resistor is just pulling sideways on the horizontal. And this leads to a really cool insight. We actually calculate the total impedance using, wait for it, the Pythagorean theorem. I know, right? So what we do is find the final outcome of that tug of war between the inductor and the capacitor for one side of our triangle. We use the resistance for the other side, and bam, the hypotenuse gives us the total impedance, Z. So we've got this constant tug of war going on inside this circuit. But what if it was a perfect tie? What happens then? Well, that's when we hit the circuit's sweet spot. This really is the key question, right? It turns out, at one very specific frequency, the pull from the inductor perfectly, and I mean perfectly, cancels out the pull from the capacitor. And this magical state has a name. It's called resonance. And just look what happens when we hit resonance at this one single special resonant frequency. You see it here as omega naught. The graph shows the total opposition. The impedance just plummets. It hits its absolute minimum. And when the opposition is at its lowest, what do you think happens to the current? It shoots up to its absolute maximum. The circuit becomes unbelievably efficient, but only at that one frequency. So, to sum it all up, At resonance, the two reactances cancel each other out completely. That leaves only the resistor to oppose the current, and that means you get the moment of minimum opposition, maximum current, and yep, perfect efficiency.
I know this can all feel a little abstract, so let's bring it back down to earth with a quick, practical example. You'll see how simple this really is. Okay, take a look at this circuit right here. We've got a 5-ohm resistor, an inductive reactance of 3 ohms, and a capacitive reactance of, you guessed it, 3 ohms. See what's happening? The reactances are exactly equal. This circuit is in resonance. And because we're at resonance, that big, scary-looking impedance formula, it becomes incredibly simple. The effects from the inductor and the capacitor just vanish. They cancel out. So the total impedance, Z, is just equal to the simple resistance, R. All that chaos just turned into perfect harmony. And now the calculation is an absolute breeze. We just use good old Ohm's law. The current is simply the voltage, that's 100 volts, divided by the only opposition left, that 5-ohm resistor. And that gives us a massive 20 amps of current flowing through. See? It's that easy. And that, my friends, brings us full circle, right back to our radio. When you turn that dial, what you're actually doing is changing the capacitance or the inductance inside that tuning circuit. You're adjusting its resonant frequency. You're literally hunting for that one sweet spot where the current from your favorite station signal is cranked to the max and every other signal just fades into the background. This idea of finding that perfect resonant harmony, it's not just in radios, it's everywhere. So next time you tune in, take a second and think, what else are we tuning in our world?